All right, recording is rolling. So today is Thursday, October 20th. Here's agenda stuff. So you guys know that your homework is due tomorrow. I'm going to do something for you guys. We've spent last 2 days going over some of these problems, right? So I sent you guys some problems from each of those chapters. Okay, so as long as you've been following along, you should be good to go on that front. Okay. If you want to turn in early, you could always turn in early. I just gave you guys your next Open Notes take-home quiz. Looks like this. Okay, let's have this due on Monday. And you could turn this in tomorrow, right? If you don't want to have it over the weekend, but there it is. Okay. Food drive. So, got an email. There's a food drive going on. Yeah, you guys see that cardboard box down there? Got this flyer taped to it. All right, so from what I could figure out, it looks like you have until November 18 to bring stuff in. So if you throw stuff in the box, then I will take that where it needs to go. Somebody will be happy. Right, so
Mr. Griffin,
yeah,
I didn't get a take home quiz.
Oh, all right, here you go. Quiz. All right. So main thing today is going to be this lab. I gave you guys this lab page. You walk in, so you guys like this. But right before I hit that, I want to do another rotation thing, sort of related, not exactly, but some of the thought process. So I flip my screen over and walk you guys through this here. Okay. So cars on wall. All right. So this one I like a lot. I've been wanting to get to a problem that looks like this.
Oh yeah, this thing.
Get this fixed up here. All right, so so you guys see those motorcycles going around that banked wall, and that's a really steep banked wall. I mean, it's not exactly vertical, but it's getting pretty close up there, right? I don't know, maybe it's like 70 degrees to the horizontal. Maybe, you know, I'm just kind of eyeballing it, maybe. Okay. And what question I was going to ask is, how about this? Let's go back to the motorcycles. There's motorcycles. See, if those motorcycles are going too slow, they kind of tend to drift down the wall. If they're going too fast, they kind of tend to drift up the wall. But there's like some speed that'll keep them not in true static equilibrium because they're on a curved path. So there is always a net force, right? But you could sometimes you hear the term dynamic equilibrium in the sense that like the radial size isn't changing or they're not really drifting up or down the wall, right? There's some speed they have to go at, right? And a good question could be, well, what about the cars when you get the cars going? Because the cars are obviously way more massive than the motorcycles, right? So I was going to ask you guys, should the cars go faster, slower, or the same speed as the motorcycles to like maintain their position on the wall? But you guys obviously see the answer is they're all going about the same speed. I guess that, which is kind of a hint to the answer. Like the question could be like, what is that speed, right? Given maybe like the pitch of the wall, what angle is the wall at? Maybe what planet are you on? Like the gravity field, that probably matters. Possibly the mass of the vehicle, although it's looking like the mass is going to cancel out, right? Because motorcycles and cars are all going at the same speed. Or how about the radial size, like the size of the circle they're on, with that radial size, right? And so there's some expression that can link these together and maybe could like solve for speed, right? So I want to take you guys through how to solve such a problem. So let's switch the screen back over here. Okay, and we're going to do this just to save a little bit of time so you guys can have a lot of lab time with each other to do lab later. It's just the whole solution's right here. Okay. This is not the only way to solve it. This is one way to solve it, sort of like the conventional way, right? Where we're and then inertial frame of reference is like from the point of view of the camera, right? And this really just means a non-accelerating frame of reference, right? So like if you're inside the car and you're blindfolded, you'd have a different experience, right? You would be in an accelerating frame of reference inside the car, but we're outside the car. We're from the point of view of the camera. From the point of view of the camera, there are really only two forces on this car. There's the weight pulling it straight down, okay, and there's also a normal force on the road. Now, so far in this class, I think we've always had the case where the road was basically flat, in which case the normal force just balanced out the weight, right? Although I do remember the other day we said, well, if the Earth is spinning or like some latitude close to the equator, that you guys remember there's technically like about a 0.5% difference between the normal force and the weight, but we usually just throw that out anyway. But that's not going to be the case here. Right? I could have asked you guys, but you guys see kind of where this is leading. Would the normal force be greater than or less than the weight? Yeah, you guys see this vector is a greater magnitude than this vector, right? Which maybe kind of makes sense because if you're like wheeling around a circle like closer to the centrifuge, right? Yeah, that car and that road are really pushing on each other really hard, and this is the force on the car from the road, isn't it? Okay, so the force is on the car. There's only two forces: the weight down and the normal force, which is perpendicular to the surface. Okay, and it is some kind of balancing effect where, see, I don't want the car to really like drift up or down. Okay, right, so one way you could solve this is you could take this normal force, break it into components, and say, well, that normal force is partly holding the car up, and which thinking ahead a step should balance out this weight, right? Okay. And partly pushing the car in, which acts as the net force. The fact that the car is on a curved path. You guys see that the car is like going into the page, like going around. You guys see the taillights on the car. Right? It's like going into the page on the curving around, right? Like kind of behind here. Okay. And so it looks like some component of the normal force is acting as the centripetal force, which is the net force. There's a net force on the car. It's on a curved path going around. Right? Okay. Right. So I can set up a couple of algebraic expressions and solve. I mean, the whole thing's solved right here. Right? The solution is like so quick you can get it. Right? So do you guys see just by eyeballing it that this angle and this angle is probably the same angle? Like if that's 71 degrees, that's probably 71 degrees, for example. Right? Okay. Probably believe that, right? Right. So one expression is the one I pointed out already, right? That the normal force times cosine of this angle. So the cosine component of the normal force is equivalent to the weight. That's balanced out. So that's this expression right here. Normal force times cosine theta is the weight. Right. And then how about the actual net force, which is the sine component of the normal force, right? Normal force times sine theta kicks over to opposite. Right? That is the centripetal force, right? That's what's allowing the car to go around a curve, right? So that's that expression right there. Okay. Just make this perfectly clear, in case you're wondering what each of these things are. Okay. So m is mass of the car, v is the speed of the car that maybe you want to solve for, theta is the angle of pitch of the wall from the horizontal, g is the gravity field, and r, this r right here, right, is the radius of curvature. So maybe like the far left side of this paper, you guys see like a dashed line right here? It could be like the central axis that the car's going around. See the car's kind of like zoom, 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 like sort of about this axis right here. Okay. That's why I labeled this r. I see r. Okay. That's what that r is. Okay, so I have two expressions, this and this. Okay, so which is just this and this copy pasted, right? This is a system of equations. Right? Here's one equation. Here's another equation. Right? And then I put a bracket, a curly bracket to say like a system. This is a system of equations right here. Okay? Now, there's different ways you could go about like solving this, right? But one way, just very simply, a completely legitimate algebraic step is just divide the two equations. Because if you divide the two equations, the normal force cancels out. Right? Probably wasn't super interested in that start with, although you could later solve that. And, hey, the mass of the vehicle cancels out, which matches the empirical evidence of the video, because all the motorcycles and cars were all going to the same speed regardless of their mass. Right? That's what the mass canceling out means, right? Right. Guys, what is sine divided by cosine?
And
Tangent. Boom. Tangent of the angle is, and then that simplifies to this expression. So I see four variables floating around in this expression: the angle of pitch of the wall, the gravity field of the planet, this radius from the central axis, and the speed of the car. If you had any three of those, you could solve for the fourth variable, right? So if you knew bam, bam, and bam, you could like solve for the v. A couple more algebra steps. Guess that. All right, so now we have an expression to link this all together. Okay. I will do one more thing with you guys. I'll flip this paper over. Here's a completely different way of solving the problem. Now, this is from point of view if you're inside the car, right? And the faster the car is going, you think there's a centrifugal force pushing you out. Now, that's a term I almost never use in class, centrifugal. I always say centripetal, right? Which is like this component here, centripetal, right? But if you're inside the car and you're blindfolded, the faster the car goes, you think you're being thrown outwards, right? You can actually solve it from that point of view. It's called dynamic equilibrium, right? Dynamic equilibrium, it's not true equilibrium. Cars are on a curved path, but if you didn't know that, right, you're just trying to not drift up or down the wall. That's sort of like a type of equilibrium, right? But it ends up being the exact same solution. It's the exact same expression. It's how it works out. Okay, so anyway, that's there. Oh yeah, good. Yeah. Good. Right, so this is being recorded. I'll throw this on Google Classroom. If you're really intrigued by this problem, then again, it's a real short solution. Right, so, you know. But let's get to our main thing today, which is this lab going on. All right, so you guys have a task today to figure out what is the coefficient of friction between two surfaces using a turntable. Okay, so I've got lots of objects around. You guys probably see all the stuff around the lab table. We got little masses. There's picks, there's like little pens, you might find the thing, right? How about the line acids, different materials, right? Those are different materials, right? Right. There's some coefficient of static friction between, say, this wood surface and each of these materials individually, isn't there? Coefficient of static friction. And that has something to do with like, is it the friction force actually holding each of these objects right now in a circle? Right. Oh, you know what's going to do here? Let me break out the Roosevelts again, because I want you guys to see this too. Right, so all these Roosevelts are identical, math, material, whole deal. But they did put them at different positions. Some were really close. This guy's really close to the center. Here's the center dot right here. Here's the center. Right. This guy's only a few centimeters out. Right. This guy's so many more centimeters out. Right. So maybe the position of this possibly matters. Right. Let me give this a spin. So right now, friction is the force that's holding all those objects on the surface. But if they go a little faster, there's an object flew off. That object flew off. Ooh, the outside Roosevelt flew off. Well, here's where the position probably matters, right? Because these Roosevelts stayed on, right? I have to probably go a lot faster to fly these off, right? That guy's still the holdout. He's the last holdout. Right. So, something to do with this, the spin rate. I bet if you knew the spin rate called angular velocity, there would probably be enough information where you could, in principle, calculate what is the coefficient of friction between two surfaces, right? Okay. And that is what you guys are trying to get at. Okay, so let me take you through this page and get you guys set up, and then you'll have the rest of the day to work with each other and figure out coefficient of static friction. Right. So see where it says trial. Here's what I'll have you guys do for trial. Just describe whatever item you have. So I could do like, how about this 100-gram, I'll call this like a slug. How about that? 100-gram slug. You could have like a coin. Let's say coin. You know, specify. You know, is it a dime? Is it a penny? You could have there might be a couple of guitar picks floating around from songwriting club. Right. So just find some items back there and say, I want to figure out what is the coefficient of friction between, say, these two surfaces. Right. So let's look at the setup here. Right. So here's your turntable. Right. Oh, look at that angular velocity. That's omega, right? That curly look at W, omega. It could be radians per second, how fast is this spinning, right? I had to spin it faster and faster to. Right. So how about your item? Say that that's like a coin right there, for example. Right. Well, there would be three forces on this coin. Right. Its weight pulling straight down. The normal force holding it up, which you could just say is equivalent to the weight. Okay. And if it is spinning, then the force that's allowing it to be on that curved path would be the friction force, wouldn't it? Right? Would that be true? Right. So there you go. There's the free body diagram. Okay. And you guys see clearly that this point is not in equilibrium. There is a net force, which is acting as the centripetal force, right? The friction force is the centripetal force. Okay, so that's the setup. Okay, let's dig into this table. Okay, so you've got some item you're going to test. Okay, I gave you the gravity field in centimeters per second squared. So when you guys take your rulers back there, because you're going to have to measure radial size at some point, right? Radial size, like from here to here, for example. Right. Just go ahead and do centimeters. Which is this next column right here. Okay, so you got 9.8 meters per second squared is the same thing as 980 centimeters per second squared. We did the same thing for the outlet lab, right? Radius in centimeters. So how far is this item from the center? Okay. What's the radius of curvature as it's going around? Okay. Now, you can start off spinning it kind of slow, and that whatever item you pick is going to stay on the surface. Okay. Then you do a little faster, a little faster, a little faster. And at some point, just like that demo I just did for you guys, it's going to break friction and slide off. Right, tangent to its motion, law of inertia, the whole deal. Okay. Now, at the moment it breaks friction and slide off, do your very best to maintain that angular velocity. Just try to keep it constant. You know, you might have to apply the external force to overcome the friction. Okay? And see if you can maintain a constant angular velocity. And then you have to figure out what that angular velocity is. So the way I've sort of got set up for you, because I did type a number in here. Right? Guys, 2 pi radians. How many revolutions does that represent? 1, exactly. Okay, so the number 2 pi radians represents exactly 1 trip all the way around. Okay, so did you guys bring your stopwatches today? You guys brought your cell phones? All right, all right. Right. Oh, and a physical wristwatch too. All right, well, that's it, old style. Okay. So as this thing's around, you go like click, click, right? So try to get how much time for 1 revolution. Right. Now, since time is probably one of the trickiest variables to grab in this class, that's why I have you guys do 3 times and take an average. You guys get that? Okay. Now, I'll tell you what, if you want to modify this, you can. If you don't like doing one revolution, if you want to scratch out the 2 pi and do like 6 pi, I want to do 3 revolutions, and you could do that. If you want to scratch out this number and make up your own number, that's okay. Right, so 3 times, take an average. Okay, so if you know the average time to go around once, then if you do 2 pi radians, divide by the amount of time, that can tell you how fast it's spinning, right? In radians per second, right? Of course, you guys remember from last couple weeks in this class that that's exactly how you want to quantify how far something turns or how fast it's turning. You have to have radians there. You don't want revolutions, you don't want degrees. Okay, that's one reason I printed this numbers to really remind you guys of that. It has to be in radians per second for omega, right? Okay. Right, finally, this last column, you can get the coefficient of friction. Now, how can you do that? Well, I sort of like derived this whole thing for you. I mean, ideally, if you want to get more out of this class, then see if you can do the challenge. See if you can just start with a blank piece of paper and drive this whole thing from scratch. But this is sort of like the solution anyway, right? Which is the friction force is acting as the centripetal force. Now, friction force, do you guys remember that's coefficient of friction times the normal force? Or another way to think of that is that right where it breaks friction, if you whatever that friction force is compared to this normal force is the coefficient of friction. So if you take coefficient of friction and multiply by normal force, that brings back to friction force. That's what this is substituting in for this. Okay, that's in that. Okay. Now centripetal force, you guys have an expression from your last lab. That's well, sort of. I did the omega version of it. It could be mv squared divided by r. You could go that way, but I just went ahead and do m omega squared times r, which is a bit more convenient for like turntables or neocylinders, the whole deal. Okay. So that subs in with that. That subs in with that. Okay. Okay. And then normal force. Hey, remember how that should be pretty well equivalent to the weight? I guess if you want to be really tricky about it, you see like 99.5% of the weight. But okay, you guys can do anything. Okay. Okay. So sub that in. Do you guys see that the mass is going to cancel out? Mass cancels out. Okay. Although you could test this empirically. Like I think this and this are I don't know if they're the same material, but maybe. Okay. Suppose you found different lab weights that appear to be the same material. You can actually test this. Say, hey, I wonder if these actually do have the same coefficient of friction with that wood surface, right? You test that out, but supposedly mass should cancel out. Right? And then you get this expression, and then you're one step away from bam. There's coefficient of friction. Well, I should say coefficient of static friction if you're figuring out where friction slides. Okay, that's exactly how you can calculate it. Okay? So pretty good skill to be able to do that from scratch, but that's how you do it anyway. Okay, and then you can figure out what is the coefficient of friction between say this object and the surface, this object and surface, this object and surface. Okay, guys, what's a reasonable number for a coefficient of static friction? Here, let me write a few options. Suppose you get Suppose you get you and your lab mates all come up, do different calculations, and you're all prepared. Hey, we all get different answers. And one of your lab mates gets a number like this. One of your lab mates gets an answer like this, and one of your lab mates gets an answer like this. Okay. Which one of those looks like the most reasonable coefficient of friction?
0.30.
Yeah, that middle one, right? You'll probably get an answer that's in that ballpark. Maybe you'll get 0.50 or 0.60 or 0.20, but it should be kind of in that ballpark, right? Right. So 0.30, what that means is that this would be 30% of this. Okay. Right. You guys got there? All right. So you guys got right, so just remind you guys all the assignments going on. Okay. So you probably finished the homework already. You can turn it in whenever you want. Tomorrow, if you like it, maybe you want to use it to help you out on the quiz. Remember, take home quiz I'm picking up by Monday. You can always turn it in early. You can turn it in tomorrow if you want. Right. And then this page, just turn into the gray tray by the end of class today. And you guys got the rest of today to work with your classmates and figure out coefficients of friction. Okay, and I'll walk around and help you guys out. So everything you need is back there. And I will also give you guys my demo turntable.